So the question is saying a lossless 50 ohm transmission line is terminated with a load impedance of 50 plus 25J, and it says use a Smith chart to calculate reflection coefficient, Viswire voltage standing wave ratio, the input impedance, this much lambda from the load, and yeah, we'll just get into all this. So the first thing is it says a lossless transmission line is just 50 ohms, so you could automatically know that the characteristic impedance is 50 ohms, and it says the load impedance is 50 plus 25J ohms, and this is okay. So this is our load again, ZL, and this will be our generator. Just put VG, and this is our input impedance. I don't think we need it for this question, or they're not asking for it, but it's good to know. And the input impedance is the impedance of the generator, and the characteristic impedance is just, you could kind of call it the impedance of the line if the line was like infinitely long. And they don't give us the distance of the load from the generator, or the generator from the load, so we gotta find it. And the first thing we gotta do is plot. What do we gotta do?
We have to plot, like, you have to divide by the characteristic impedance and then plot it on the Smith chart.
Why do we divide it by the characteristic impedance? Why is it ZL over Z0?
So, like, the Smith chart has different units, so to like scale by those units.
It's because it says right here.
Okay.
It says on the Smith chart you gotta divide it by Z0 and divide the J component by Z0, right? And so it's ZL, so 50 plus 25J divided by 50, which is 1 plus 0.5J. And now we're going to plot this. 1 plus 0.5J. And you start with the real component, which is this scale right here. It says this is the resistance component. And then the complex component is this axis. And if you don't know, it's R plus XJ, which is what it says. R is here and X is here. So 1 on the Smith chart, where is 1?
In the middle.
1 is right here. And, or this like arc. And where is 0.5?
Right there.
0.5 is right here?
Yeah.
Yep. So now the next step is to draw a radius from the middle point, which is here, to the dot, or the point that we made. And it has to be like a perfect line. Yeah, that's good enough. And now I'm gonna draw a perfect circle, which is my Viswire circle. Now we're gonna copy this, paste it, and just move it so it connects to help us draw the perfect circle. Should be good enough. And now we draw the circle and try to put the radius in the middle. That should be good enough. Now from this Viswire circle, we could actually find the Viswire on the very right here, or another method is we could literally just draw a line extending, and it has to be 90 degrees all the way down 90 degrees, and connect it right here on the very left side of the circle, and make the line extend all the way down. And it has to be 90 degrees, and you could see where our viswar and our reflection coefficient is. So viswar is right here, and the reflection coefficient, you don't look at this one, don't look at this, look at the bottom one. It's always this one. It's the reflection coefficient for E or I, electric field or current. Okay, don't look at the top one ever. Okay, so we could see our viswar is around 1.61, or is it known? Yeah, 1 point. So this is 0.5, or this is not 0.5, this is 1.7. So it's around 1.65, right? You see how it's 1.65? And we can see our reflection coefficient is around, so this is 0.2 and 2, 4, so 0.2468. So the magnitude of the reflection coefficient is 0.24, and the angle, the way you check the angle is, it's also labeled, it's right here, and it says the angle of reflection coefficient in degrees. It's labeled. So what we do is, from the point that we made here, we draw another line extending all the way, and we read the angle. So what's the angle?
Well, 83, something like that.
No, 70.
Oh yeah. So 77.
So 2, 4, 6, and then that's 8. So around, like, yeah, let's just say 77. So the reflection coefficient, this is for A. R is around, what was the magnitude? 0.24. Angle 77 point, like, 7. Let's just say that. Okay. Now let's look at the viswar. We already found it. There's 2 methods, and that was like 1.61 or 65. And we could always check using the formula, but I'm not going to do that here. Actually, I'll just do it. So the formula for viswar, or actually we're just going to check at the end. It makes more sense. So C, it says the input impedance 0.35 lambda from the load. So where is ZL right now?
So it's right here.
Yeah, ZL is right here. So
And you add 0.35 lambda. So this is gonna be.
is it? Well,
14.
what's the direction though?
It's towards the load.
Which direction is it?
So you're going from the load towards the generator, right?
Exactly. You're
Yeah.
coming from the load. So if you're coming from the load, you're gonna be going to eventually the generator.
Yeah.
So 0.35 lambda from the load. So where's lambda right now? Where's lambda?
Right right now is.
I mean, where's the lambda for generator for the load? Sorry.
So right now is 0.14.
Is it the top
0.3.
scale or the bottom scale? Check.
Top scale, because top scale is going towards the generator.
Exactly. Wavelength toward generator is the top scale. And yeah, we're over here. And we're coming from the load. So we're going to the generator or towards the generator. So yeah, what is it?
0.143.
0.143 lambda is where the load is. That's where the load is. And they want the input impedance 0.35 lambda from the load. So what do we do?
We add them.
So add 0.143
0.493.
0.493 lambda. Forgot that lambda there. And now just do it for me. What do you do?
So you look for 0.493. Since it's close to 0.5, it's going to be on this side, right here. And then this is 0.493 right here.
Exactly. And if you didn't watch the other video, you probably should, but the 0.5 lambda is like around here. And 0.25 lambda is around here. And around this spot, around the very right side, you can see that the resistance gets bigger. So it turns like to almost infinity. And over here, the resistance becomes really small. It becomes basically 1. Just keep that in mind.
0.
Yeah, 0. So keep that in mind for the next question. So 0.493 lambda is over here. And now we're gonna draw a line from this dash all the way to the point, like this. That should be good enough. And now to find out the actual point, you have to look at where it intersects on the Biswar circle, which is the circle here. And put a point there. Now how much is this?
It's like 0.61 and 0.01. It's like less than 0.1. So it's like 0.61 minus 0.0.
So you could even like help yourself. You could like, so that's here, and then the point is here. So this is 0.1, or this is 1, 2, 3, 4, 5. So it's around the 4.
Yeah, so it's 0.04.
Let's just say 0.041 minus 0.041.
Yeah.
So around 0.61 minus 0.041, right?
Yeah.
And that's with a J. And is that the final answer, or? So we got 0. It'd be, pay attention bro, R divided by Z naught.
Yeah, so we
And
multiply
then
by R.
JX divided by Z naught. So we have right now ZL or Z.
You multiply by 50 because you divided by 50 in the start.
Yeah, so Z at 0.35 lambda from the load divided by Z naught. Wait. Oh, no. So 50 times 0.61 minus 0.041J equals, so yeah, it was, the equation was ZL divided by, or ZL nu, I'll put a nu like this, and it was like Z naught is equal to that, and then we move the Z naught to the other side, and we'll get the ZL nu, which is around. So that will give you 30.5 minus 2.05 J ohms. So that's how you find ZL nu, or a ZL 0.35 from the load. And now we're gonna answer D. D is asking for the shortest length of the line for which the input impedance is purely resistive. So the shortest length of the line where the input impedance is purely resistive. So what does that mean?
It has the highest resistance.
So if you look at this part, it says purely resistive, right?
Yeah.
So they want Zn.
So
They don't know Zn. We don't know that, the input impedance. And they want the shortest length of the line. So you got to keep that in mind.
shortest length.
And they also want it to be purely resistive. What does that mean? We have R plus XJ.
Yeah. So there's
X is the
no-
reactance.
So there's no X.
There's no X, yeah. There's no reactance. So we only have R.
And you want R to be
So
as short as
remember on the scale,
possible.
this is our reactance.
Yeah, yeah.
And
We're
this is our
only gonna be
reactance?
on the-
So we're only going to be on,
Yeah.
this scale.
yeah.
That's what you got to keep in mind. So, yeah, no X, no reactance,
And it's the shortest line. So
only resistance scale.
So are we short circuiting?
No, that doesn't really matter. We just got to look at the Smith chart. So they also want the shortest line length, right?
So does that mean it's the short circuit?
No, we got to look at the Smith chart. So, for which the input, yeah. So look at the Smith chart. Which has the shortest distance?
0.6.
No, that's the smaller resistance. But which has the shortest distance? The shortest lambda.
Or shortest lambda. It would be this one right here.
No. Okay. So this is 0.25 line. We're on this scale, right? So there's only 2 points where it could only be resistive.
Oh, 0.25 and 0.50.
Okay, I'll help you. So we have this point in the Visual circle and this point. Let me just erase this. Actually, no, I'll leave it. So we have this point right here on the Visual circle, that's only resistive. And this point right here, that's purely resistive. There's no X on these points.
We have to find the shortest one, right?
And the shortest length. It said the shortest length of the line. What is the length of the line? It's lambda, whatever number. But remember on the right hand side,
It's 0.25.
0.25 lambda, it says right here.
Yeah.
And on the left side,
0.5.
it's around 0.5 lambda, yeah. So,
We should pick the right side.
exactly. So we picked this point. And that's around 1.61.
Yeah.
Which is it's basically our Viswar as well, but it doesn't really matter. So it's 1.61.
Is it always the which one?
No,
Oh.
it doesn't always have to be. The question's saying that.
Oh.
It just happens to be that way. So D, the shortest length of the line for which the input impedance is purely resistive, the shortest length is 0.25 lambda. And R in that case will equal 1.61 ohms. And the position of the first voltage maximum from the load.
So voltage maximum means short circuit.
Let's not worry about the circuit. Look at the Smith chart. So the position of the first voltage maximum.
So where voltage is maximum?
Yeah.
Where does it say voltage on the Smith chart?
There's no voltage, there's no current. Like it doesn't say, but think about it like this. V is equal to IR. And then, yeah, so it's asking the first voltage maximum from the load.
So if R is infinity, then V is also infinity.
Exactly. So where is R infinite?
Right here on the right side.
Exactly. R is infinite around here. Or very, very high. So then V is equal to I, and then a really high resistance will give you infinite voltage. And that's like the maximum voltage.
Yeah.
And you don't even have to think about infinity or not. Just think about what's the highest resistance number. Point at where the highest resistance is.
Yeah. 'Cause
It's here.
Yeah.
The highest resistance is here. So it's on the very right side. So where is the position of the first voltage maximum from the load?
Low position, what does that mean?
So it's this. So it's 0.25 lambda.
Oh. So it's the same as last question.
Yeah. Except they want the position. The position of the first voltage maximum from the load. So the load is here, right? Well, what is the load? The load is 0.143. We're doing
Oh, so we do 0.143 minus 0.25 to get the thing. Or 0.25 minus 0.143. Like we're measuring this distance right here.
exactly.
Yeah.
So would it be, which way is it? Say it again.
I think it's 0.25 minus 0.143.
Exactly. That's correct. And that should give you, how much is it? 0.1.
So it's 1,
1,
113. 113.
Yeah, lambda. And that's the distance from the first voltage maximum from the load. And what is from the load mean?
It means it's coming from the load and going to its generator.
Yeah, so you're coming from the load and you're going towards the generator. And that's means we're going this way. It says wavelength toward generator, this way. And we look at the top numbers. So yeah, that's pretty much it for this problem.